I'm very happy to be here.
Yeah. So we have Per Mykland as our plenary speaker today, and this is the last session of the 7th StatFin. And Professor Mykland is a professor of University of Chicago, and he is also the scientific director of the Stefanovic Center of Finance. And he will talk on non-parametric observed standard errors for high-frequency data. Ben, please go ahead.
Thank you, Ritu. And thank you again for having me at the conference. I'm very happy to be talking here. And so this is a problem that we have worked on for a few years. It's but it's an attempt at doing something very general and something that works in all sorts of situations. But at the same time, it's slow, and we discover new things and about it as time goes by. So this is the latest installment in this saga. I will refer back to things we have published already, but I will also talk about things that we have not yet published, and the main focus of the talk is about things that we have not yet published. But I thought I should give some of the background, and that is, so I'll start with that. So I'll talk a little bit about, the why high frequency data. I realized that other speakers who are talking about high frequency data in this conference, and many of you work on that, and of course Ritu also works on that, and so there are many of you who work on that, but I thought I should still do a little bit of a recapitulation of the whys and the wherefores, and then after that I'll get into the question of what we have called observed AVAR. I should say that we chose the word name observed AVAR because we thought this would be particularly easy to understand in a broader community. Those of you who have very central core knowledge in statistics may find that you would like me to have called it something like observed, or I don't know, not exactly likelihood, but it's close to observed likelihood, but it is not yet observed likelihood. And so we'll take that as far as we have time, and then that will be the talk. So just begin with the issue of data set, and this is just an arbitrarily selected medium liquidity stock in the US market. So this is the US Merck, not the German Merck that we talked about. And this is just the number of transactions, which we just, it's not, this is not anything rigorous. We just took the data number of transactions on the first Monday in April of each year, and you can see that this goes up, and you can see the financial crisis around 2008, and then you can see that there is some pullback after that, and then there's a lot of action, and things have been going up. The fact that this curve is not very smooth is just means that we haven't smoothed out a lot of things that have to do with different companies and different days and so on. So this particular stock at this point is approaching 100,000 transactions per day. If you go to Apple, you're going to see a couple of 100,000. If you go to transaction, so that's transactions. If you go to quotes, you can probably multiply that by 10. There are also a number of things, index related securities that touch, I think, close to a million transactions, if not more, per day. For example, the S&P 500 future, there's one of the exchange traded funds related to that is the SPX exchange traded fund, and that's they are well above 1 million per day. Looks like at this point. So we have very large data size. it turns out that the data size is maybe not quite as large as one thinks if one starts taking into account microstructure noise. So if one starts wanting to estimate things that are less standard, so for every data size, there's always something one can want to estimate that is still difficult to estimate. But that's another story. Yeah, so we have very large data, and so the way I should say that at this point, high frequency data, of course, is everywhere. And I'm talking about financial data with trades, quotes, options, order books, etc. But you have neuroscience, survival analysis, geoscience, climate reportings, wind measurements, turbulence, and of course, in particular, we have internet data, payments data, Twitter data. You have, so in with the growth of the internet, the amount of data is of course increasing hugely, and it's not just that we have high dimension, but we also have high frequency, and so this is where I now keep saying that so in financial econometrics or financial statistics, we started looking at this. People started looking at this in the late 90s, and we started looking at this in around 2000, and but the world. So our claim is that the world is catching up with financial econometrics. Just a couple of words about what financial data there is out there. So I mean, first of all, you have this very high frequency data. I mean, it depends on the liquidity of the stock. So some stocks are not high frequency, right? They're not traded often. But so you have transactions that are tick by tick, and from TAQ. Here it says Reuters. I should have said Refinitiv, which is the descendant of Reuters that does data. And you have quotes, bids and asks from the same sources. And these particular databases, TAQ and the Refinitiv data, are typically available at universities. Then you also have such things as limit order books. You can have, there are also such things as futures data, currencies, and so on. And some of these are widely available, and some are not quite as widely available. So, but a lot of them have very high frequency. You can imagine currencies, for example. So the situation is we have almost continuous situation. There is typically microstructure noise, so what the finance world is calls microstructure noise, and what in the statistics world might also almost be called observation error. I mean, if somebody makes a trade about a stock, it's a little bit optimistic that they can find the exact price, even if they're trying very hard. So there will be some error, and there are various models for that. Observation times can be, of course, then also irregular typically if trading is irregular, and it's asynchronous for multivariate data in the sense that trades do not happen at the same time for different stocks, for different securities. And it's often high dimensional, and it's not just that. I mean, in the US alone, there are probably 6,000 traded stocks, and when we take into account the rest of the world, it must be way beyond 10,000 traded stocks. And then on a lot of these stocks, there are then order books, which would then be an additional dimension for each stock. And then for many of them, you will have options, which, if you think about that as a function of strike price, that becomes another dimension. So the dimensionality is quite large. Now, so why is this interesting? I mean, one can use it to price assets, to construct trading strategies, but also to forecast on a number of things. And it also helps to investigate the underlying theory. One of the main things that we figured out relatively early was that what's called the fundamental theorem of arbitrage, of no arbitrage, does not seem to hold literally in the data. It's pretty close, but the difference is then this noise. and you know, we hope to be able to I mean, a revolution is happening in this area because of the data, and it's going on. So let me go to the high frequency setup that we'll be talking about, but it only affects what we're doing in a very in a slightly distant way, for reasons that I shall explain. So we have observables, and typically then sampled from a semi-martingale. And then you want to estimate a spot parameter. You think that these processes are governed by spot parameter processes theta, and it's typically a non-parametric problem, so that if theta depends on t, then it's time varying, and typically itself, we have modeled that as an ether process. One can model it differently. Now, so the typical example would be, you know, when dx has a drift term mu, volatility sigma, and then jump term dj. And examples of this would be volatility, so sigma squared, semivariance, leverage effect, which is the relation, shall we say, the covariance correlation between x and sigma or sigma squared. And so typically when x goes down, sigma goes up, so to speak. And I should say that I'm thinking about x in this context as being a log stock price. For other, so typically it's a log price that we're talking about, but it doesn't have to be. You also get high frequency regression coefficients, for example. So there is a variety of things that can be extracted from high frequency data. Now, typically this is done in the following way. So we have a spot process, small theta, and typically what's being estimated are integrals of the spot process, and for a variety of reasons. So in our plots, a spot process will be sigma squared, the volatility, and so we're estimating something that's very close to a variance, integrated volatility. You can also use the same integrals to estimating spot values. So the estimator actually is the same, but the variance will be thought differently when you do when you estimate spot. There is you get an extra term for variance in the case of spot. Now for example of something that has very similar structure is in survival analysis, where cumulative intensities and regression extensions of those, they follow the Nelson-Olin estimators, and they have essentially the same form. So this structure is not unique to finance, and so survival analysis often has a more complicated time structure. You know, do you measure time from when is it clock time, or is it time from when a patient entered the study, or what is it? So, and depending on that, you could get other situation in survival analysis. Okay, so so the problem here is the uncertainty of theta and how to set the standard error of an estimator. So we just assume that we have an estimator of this integrated theta, so big theta over an interval, and there is a usual way, a traditional way, which is to find the asymptotic variance, which is relatively yeah, I'll get back to that. Our proposal is the so-called observed AVAR, which is a direct formula for estimating observed AVAR, and in many ways, and this talk will be focused on a continuous time observed AVAR. So the data are not continuous time, but they do arrive in continuous time, and after some reflection. We originally did this in discrete time. After some reflection, continuous time seemed to be the easier way to do it. And this is important for I mean, you want confidence intervals tests, you want feasible statistics, you want forecasting models. It can be used for optimized tuning parameters and so on and so forth. So that, and I think the stand area may even go into the I mean, if you do trading, there are ideas about trading based on not just on the estimator, but also on the stand error. So there is the stand error is very, very important. Now, so just go back to the usual way, and this is the way that's still most common. So how does one find the asymptotic variance of theta hat? Well, you have an estimator, first of all. Then number two, you do you have to carry out the asymptotics and to find the AVAR and so on, and then you need a feasible estimator for the AVAR. So 2 is very is hard work, and 3 can be very difficult. I mean, it may not, even if you can find the mathematical expression for the AVAR, it can be rare. It's rare to actually pin it down. It's typically harder to estimate the AVAR than to estimate than just to find theta hat itself. And so in particular, we can see this in the literature on high frequency estimation, because most of the literature is about, so it is about estimation without taking into account microstructure noise, even though it is almost always there. And a big part of the reason for that is that people feel the need to give asymptotic variances, and they're very difficult to find in the case of when you have microstructure noise. So for this reason, there's a large class of estimators for which there are very few known, for which AVARs are not known and their estimates are not known. And so the anecdotal evidence from literature is that this path of estimation followed by calculation of the asymptotics followed by estimation is actually a very hard path. So what we will do is that we'll talk about the observed AVAR, which, so in some sense, if you want to talk about the traditional way of estimating AVAR, it's a little bit like estimated expected information, and the observed AVAR is a little bit like observed information. So I'm not arguing this on the basis of on any philosophical basis. Maybe one of these days I will try to do that, but most importantly, it is it's just easier to implement. And for those of you who have heard me talk about observed AVAR before, so what's new in the continuous time development is that you get a reduction to one tuning parameter, which is very, very nice. Better understanding of the conceptual basis of observed AVAR to a great extent because of this going to one tuning parameter. Computation is easier, and we're now getting empirical results that are actually easier, that induce more confidence than what we had before. So I think that in some sense it's a lot closer to being applicable. I mean, I think what I'm talking about today can be applied, and I'll explain what I mean by that. There's also an easier theoretical analysis if we get to that. Okay, so here is the first order story. So what we do is that we take our estimator, theta hat, and so you look at windows of size delta, where delta is a number that's small but not too small, and we have been using the range from 7.5 minutes to 30 minutes as reasonable choices for delta for setting variance for setting standard errors in daily volatilities. And so you take the value in one time period of length delta, and you subtract the value of the estimator in the previous time window, and you just integrate over dt over the whole. So we think about this as being a day. Big T is a day, and but it can be something else, and that gives us something we have called QV delta. And this AVAR to first order is 1/2 of QV delta. Now that's a little bit conservative, as we shall see, but it worked quite well, and I'll explore other ways of doing it. So this theta, so theta hat itself is observable, and so therefore the AVAR, I mean the QV delta quantity is also observable, and so by approximation the AVAR is also observable, and so one can do this. I'll explain how to compute it in a couple of slides down. There's single tuning parameter delta, and that reflects edge effects and the volatility of the spot process theta. There are several approaches to determining delta. It's possible that the most sensible thing is to average across a range of deltas, it's also possible, and this is what we have looked more at in the past, it's to use multiscalar regression estimators, where you try to separate the AVAR from the volatility and the edge effect. Okay, so for those of you who have heard me talk about this before, I mean, so it's in any case it's still non-parametric. You can estimate not just the AVAR but the volatility of the parameter process, and theta can be any semi-martingale process. I've already been mentioning the analogy to estimated expected information versus observed information. It's not the same construction. So likelihood and AVAR can be random, of course. But it is similar to bootstrapping, subsampling, and the Olin, Barnett-Nilsson class of estimators that work very well for survival analysis, and sometimes can be used for high frequency estimators. So the analogy is mainly that what it is it's an algorithm, if you like, to provide an estimator of standard error or squared standard error that doesn't depend on knowing what the asymptotic variance should be. And in this, it is similar to bootstrapping, for example, and of course, observed information. Now, just to establish right away that this is computable. So I have a formula here for how to compute QV delta of theta hat. So this is be 2 times the to first order, 2 times the asymptotic variance. It isn't very beautiful, this, but what it is this is just to, I mean, it looks a little bit like a messy formula, but you know, there's no doubt that the computer can do this without too much pain. An alternative is to use a discrete time observed AVAR, which is the one in the first formula here, and you at that point you can approximate the continuous time AVAR with the earlier discrete time AVAR. The continuous AVAR is really based on the insight that in discrete time AVAR, K and delta T are really I mean, they do very much the same thing. If you multiply them together, you get delta in the limit that will give you QV delta, but even close to the limit, you're getting something that's very similar. So it's computable. This also highlights that there are sufficiency considerations for using the continuous version here rather than the discrete time version. So let me go to the statistical setup. So we define, as before, we define the parameter, if you like, as the integral of the spot parameter, and we do that for any interval from t to s within a day. So again, this is, you can think of this as a day, but you know, it could be a week or it could be less than a day. So the typical situation is that the difference between theta hat and theta is so it's there is a martingale, and then there is an edge effect, and the edge effect is has to do with the phasing in and the phasing out of the phasing in of the estimator at the beginning of the time interval and phasing out at the end of the time interval. So this is a edge effect that almost always with us. I mean, anything that's done in time or done in space typically has an edge effect, and it looks a little bit like noise, and it is a little bit like noise. It tends to go to zero as number of observations go to infinity, unlike the noise. But on the other hand, it's modeling wise, it's much harder to describe it. But it does seem that one can do relatively meaningful things with it. Okay, this just to say that you can create additive estimators typically in these high frequency situations. In the 2017 paper, we went over a very large number of papers, of other papers to see how, if the AVAR methodology could be used for the sort of the main examples in high frequency econometrics, and we established that. So this is published in the 2017 paper. There's a little bit more in the 2021 paper. What I'm talking about does actually work, and I'm going to impose conditions for the asymptotics, and in these examples, those conditions will pan out, they will work. Okay, so let me get to the heuristic here, which is that if you think of the difference between theta hat in one time interval from t to t plus delta, and then minus one time interval going back delta from t, well, you get an estimation error and an estimation error, and you get the change in the value of the parameter. And what happens in most circumstances, and there can be exceptions to this, is that the estimation error is much larger than the change in the value of the parameter. So if you take these estimation errors, so you can square the whole difference, get a squared estimation error, a squared parameter behavior, a squared estimation error, and cross terms that are, because they're closer to second order martingales, they are less they're second order typically, so with the parameter behavior, one can then either one can build that into the process, or one can try to, or one can try to get rid of it. I'll explain. So if you use this approach, and of course there are proofs to see this and so on, you find that the QV delta, so you can write it as estimation error plus parameter behavior plus cross terms, and this can then be further related to the a QV delta based on the martingale, and again the change in the parameter behavior, and then at that point you have the cross terms and you have edge effects. And if you write that all down at the bottom, so if you take the quadratic variation of the martingale to be the same as the AVAR for any number of observations n, then you end up with this result here. And Now, right now, it looks like if you can take delta to be as little as you like, but that's actually we shall see that runs into the edge effects. But what we have here is we have the estimation error and the parameter behavior, and this really is just from taking the square of this expression and just trying to study it a little bit further. And I'll get back to the conditions for this to be true. Okay, so the examples of edge effects, I think that would take some more time, so I'll skip that. Now, if you have edge effect, then this is the same thing as I had before, but now I also have an edge effect in the QV, and I'm mentioning what the variance terms may be. So what you can see is that the if you just want to minimize with respect to delta, so the two terms that you don't want with respect to delta, it's optimal to take delta away from 0, and that looks like it's true in data. So strategies for AVAR, one is then to say just that if you have a reasonable choice of delta, you say, well, the volatility of theta is actually very small. The bias due to the edge effects is also small if you have a good delta. So it's slightly conservative, but if you take AVAR to be QV delta or an integral over several deltas of QV delta, then maybe you have a good estimate. One can also do a exact reconstruction of 2 or multi-scale regression estimators, and by actually also estimating the volatility of theta and the bias due to the edge effects. This is the data doesn't cooperate quite as well on that. Mainly, I think, because the volatility of theta typically has a very large estimation uncertainty. So just to show you what this might look like, I hope this is visible. What we have here is okay, so this is the QV, which doesn't necessarily, I mean, the absolute numbers here may not mean much, but this is a scaled QV, which is QV divided by TSRV squared. So if you want to take the, if you want to think of the standard error, so it's standard error squared as a percentage of, sorry, it's QV. It is standard error squared as a percentage of TSRV squared. So if you want the standard error as a percentage of TSRV, you just take the square root of this, and so you get numbers that are actually quite believable. You also see that there is an issue. So there is one day, the first day of January, seems to have particularly high estimation uncertainty for Apple, and or maybe it is the volatility that's kicking in. It's hard to say. And but otherwise, these values are very moderate. You get very good standard errors as a percentage of the thing to be estimated. This is Bank of America and Microsoft, and this again January 2017, and you can see that again, if you scale, you get numbers that make a lot of sense. Now, if you go a little bit more deeply into this, this is the scale QVK across days and case in January 2017. So we have a lot of plots like this, and the thing that's so the K values are essentially the same as the delta values. K is measured in minutes. So K goes from 30 to 80. K is 15 second is the 15-second intervals, so that the lowest K is 30, the lowest delta is 7.5 minutes, and the largest delta is 80 divided by 4, which is 20 minutes. And what you can see is that a number of curves do have the U shape, or do at least rise as a function of delta, but not all of them. For example, this one up here. So, and again, we attribute this to maybe to some extent to estimation uncertainty, and to some extent to, well, in particular to the estimation uncertainty in the volatility of the volatility. If one averages across a whole month, then you get a curve that is now increasing. And so this is Apple, Bank of America, and Microsoft. And this is so I think what this is saying is that the effect of the edge effects, the effect of the edge effects, sorry about that, is they happen to they're outside this plot. They happen below 30, and what you're seeing is therefore an increasing curve, and the increasiness reflects the volatility. That would be one way. If you wanted to use 1 month to estimate the volatility of the volatility, you could do this from this plot. We're hoping to bring that down to a week, which is probably the best thing possible for volatility of volatility. So the problem with combining, I mean, the AVAR, you would like to have it for the same time period that you have an estimator, typically daily, but for the volatility of volatility, one probably has to be contented with a week, and so exactly how that is optimally combined is a little bit still of a question. So we have various solutions in earlier papers, but they are so it's easy enough to write down solutions, but we still haven't landed on a solution that we're completely happy with. But meanwhile, I mean, you can still just take AVAR to be an integral of 1/2 cubic delta over an interval, which could then be let's say from delta goes from 7.5 minutes to 20, and that seems for most stocks to actually be very meaningful. It may depend on the so exactly how you choose your interval for deltas will depend on the liquidity of the stock, and we would prefer to have an automatic way to do that. We don't quite have that. So this does work for these stocks, and again, it looks a little bit more messy than it is. And we also thought that from the getting standard errors that are 10 to 20% of the estimator for any given day also seem to give a lot of confidence. They're relatively stable at that level. And so we think this gives a lot of confidence that the estimates actually do mean what they should mean. Okay, finally, central limit theory. We don't have a lot of time. We make an assumption, which is similar to the sort of assumption you might make in bootstrapping or for observed likelihood, which is that there is an asymptotic, that the underlying martingales do converge and to limiting martingales and so on and so forth. So it's not like, I mean, that is either true or not true, and depending on the precise estimator and the precise data, that may or may not be true. So our claim is not that we have an automatic solution to that. The claim is that you don't need to know the asymptotic variance of the martingale. In this sense, it's very similar to bootstrapping and to observed likelihood. We have an asymptotic analysis that's now in continuous time, and it's actually easier to carry out in continuous time. You can write the difference between theta into nearby intervals on this form, and you get you can then further operate on that difference. So what you end up with is a main term, which is simply it's essentially this two quadratic variation of m, which is the asymptotic variance, and delta squared 2/3 times the volatility of theta. And then we have additional error terms, which give and that gives CLT terms. I think I will skip this, but just to say that what those additional CLT terms look like is this. And so in the end, you get a normal term, stably normal term. That's that this variance is the volatility of the asymptotic variance. That's the red term, and the blue is the volatility of theta. So these are. It's not. I don't think one actually wants to use these higher order, or it's not clear that you can very easily use these limit results. But it's nice to know that they're there. It's nice to know what the rates are and the approximate neighborhoods, approximate sizes. Okay, so conclusions. Since we are headed towards the end at this point, so we're arguing for this continuous time observed asymptotic variance, and so it's a way to assess estimation error, standard error, and with the by being in continuous time, by having one nuisance parameter only, the delta, it's much easier to see what's actually happening. For this version of observed AVAR, the computation is relatively easy, and also the one tuning parameter means that you end up graphing your empirical results on one in the delta, on the delta axis only, and so again you can observe very clearly what's going on, and it also gives easier theoretical analysis. So in terms of what we did earlier, it's I mean, we use this integral to spot device that was used for the original AVAR. It's possible to do things of the small and big edge effect, slightly different procedures, and we now have limit laws for AVAR and for the volatility of theta. But I think the main conclusion is really that, if I can go back to the original this slide here, is that if you're willing to if you are willing to take the methodology to be a little bit conservative in the asymptotic variance, you simply use 1/2 times the integral of QV delta over some deltas, and you actually have a very good estimate. And so it can be used as it is. So it is available. It is available for use. It's not just a theoretical construct, and you do get results that actually look very good, but when compared to the value of the estimate. Okay, thank you. Any questions?
Thank you. Actually, you're on a very good slide. I don't quite understand the interpretation of this right-hand side, the ratio to the TSRV, and how you interpret that.
Yes. Okay. So the I should be clear about that. So the QVK. So to get to the standard error, you would divide by 2 and you would take the square root. So if you look at the scale QV here on these two scales, you would divide by 2 and then take the square root. So you know, if you get for example 0.05, right? So you would, or if you get let's say that you get a rather large number, which is 0.2. In that case, you divide by 2, you get 0.1, and then you take the square root of 0.1, and that would be your standard error. So that it's a so that you go, I mean, on the scale you get, I suppose these are values from about point stand error as percentage of estimator are about I mean, they go almost down to 0, and then they go up to what is the, I mean, that's maybe an unrealistically high. But you most of this is in the range 0.1, 0.2. I mean, so 10 to 20% based on data for 1 day, and that's quite standard in terms of what you expect. I should have made the slides with the stand errors, but
other questions from the audience?
Yes, I have 2 questions actually.
Yeah, go ahead.
So yeah, nice talk, Per. I guess I haven't seen you in a while, so it was good to see that you're still working.
Good to see you. Good to see you. Yes, indeed.
To see all the improvements that you've made. You know, I know that you know, I was there when you were when you've been starting to work on that. So yeah,
right.
I have two things. One is in the theory. So yeah, I remember in your first paper there was a little bit of like problems with edge effects. Do I understand that now you've shown more theoretical results on edge effects, and how does it help with examples, or like, yeah.
Right. Did you, was the question about how the edge effects
yeah, so what did you show, like some general results on edge effects? Do I understand that, or is it just case by case?
We have a 2021 example a paper in JOE where we have we make just some assumptions on what the edge effects are like. You know, that they're mixing or something like that, and of course then you can get results, right? Okay. So so you could say that that's a cop out. I wouldn't necessarily disagree, but so the problem is that they depend so strongly on the estimator that it is very hard to give a very general description of the edge effects. So finding a good solution to that is difficult. But so we've tried to do something a little. I mean, first of all, we looked at it in a lot of examples, right? And there it's okay. And then, you know, we had the theorem under mixing conditions under what we call large edge effect. I think the main proof is really in having checked it out in a lot of examples that yes, this does work. The edge effect is such and such, and you can control it. And so what's on this page is really just that, you know, if you have a rolling block estimator, for example, that there is a relatively straightforward a formula for edge effects, and if you have a nested block, you get something very similar. So yeah.
Okay, so
that is a patchwork.
Yeah. So yeah, it looks like it was hard work. So yeah. So with those assumptions, those 10 examples are the edge effects parts of those 10 examples are corollaries of the assumptions, or is it still, yeah, like there's still like these edge effects you split in 2 parts, and one is you know, included, and then you have to work out still the rest, or
what do you mean by included?
yeah, maybe no, it's fine. Like yeah, it was just you know, thoughts. So yeah. Anyway, yeah, congratulations on doing this. This is really I think very good work. Okay, and
Thank you. Actually, you know, I should be a little bit clear, because I don't have the conversion formula in my head. But if you have a so in this question here, on this scale,
yeah,
if you have 0.08, that corresponds to so you divide by 2 and you take the square root, okay, and that gives you 0.2. So at 0.08, the stand error is 20% of the TSIV.
yeah.
Okay, and so which is entirely comfortable, I think. For this Bank of America case, you have a you can see that the standard error goes actually quite a bit further up, so it might actually go to 0.3 or 0.4. Whereas here you're more in the same zone, where actually the standard error is mostly quite a bit below 20% of the TSIV. So I think that's meant to address Rita's question a little bit better. Yeah.
Yeah, no, this looks good. This was good. Yeah, good empiric work. So yeah, no, I understand. Yeah, you made a lot of progress. So that's really good.
It's slow progress because it is it's actually quite difficult, and you don't exactly know, if you try to step in some direction, exactly what's going to work. Yeah, it is, and then you know, then you look at data and you look at this and you say, what does this mean?
Yeah, yeah, there's so many ways to you know, you could probably write 10 different papers on this, you know, and still
I hope not.
Yeah. So
this is paper number 3. So yeah, but I think we are close to being at the end of the road here.
Yeah,
and it is, I have a lot of confidence in using the estimators that I'm proposing.
okay. So yeah, so maybe next time you have a talk, it will be on number 3 or number 4.
Well, I think maybe it will be something else.
Okay. Yeah, thank you.
Thank you.
Any other questions? Okay, then let's close the session, and thanks a lot, Per. It was very interesting.
Thank you again.
Thank you.
Thank you.
Bye.